Okay, so ladies and gentlemen, this is everything that we've covered so far in Chapter 6 about randomness and probability models. So maybe you want to put a lot of this into your notes. Please still refer back to your book and look at the examples that they have and everything that they have in the rectangles that usually indicate something that's very important. The first thing we want to talk about is random behavior, and if it's at the very beginning of this chapter, it's random if individual outcomes are uncertain. For a large number of repetitions, outcomes are regularly distributed. So kind of remember that. So that large number of repetitions is very indicative of what random means. Okay, so over the long haul. And they give an example here. If we roll a dice, I can't predict with any certainty what will it land on that first time. But if I roll it 60 times, I can expect 1 10 times, 2 10 times, 3 10 times, and so on. The probability of an outcome is the proportion of times that it would occur for a large number of repetitions. Okay, so I'll pause here, let you look at the example, and then we're going to continue on. Okay, the next thing we're going to talk about is the set of all possible outcomes of an event is the sample space S. And remember how we wrote this in class. Like at the bottom of this page, S equals, and then we use braces, and we put each one of the outcomes listed, and we separate it by a comma. And remember, if there's an outcome that occurs twice, we don't list it twice. Okay, so we just list it once, and then we'll assign it a different probability. Okay, next, an event is an outcome or a set of outcomes from a sample space. So when we say this event happens, it's something that would have been inside the braces. So if we look at the very top of the page, the 3 is an event. That is an event that would occur, and it's listed in our sample space. And example 1, when flipping 3 coins, an event may be getting the result H, heads, tails, and heads, HTH. In this case, the event is one outcome from the sample space. And remember that we use the fundamental theorem of arithmetic to calculate the number of outcomes that we could expect in that sample space. And remember, a coin has 2 outcomes, heads or tails, and if we're flipping it 3 times, then we have 2 times 2 times 2, so there will be 8 different outcomes in the sample space. So look back at your notes at the fundamental theorem of arithmetic. It's in your book. It's in one of those rectangles that I told you to refer back to. Example 2, when flipping 3 coins, an event may be getting 2 tails. Okay, in this case, the event is a set of outcomes with 2 tails. So we have heads, tails, 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 heads, and then tails, heads, tails from the sample space. These are separate events, and so we would list them separately in the sample space. An event is usually denoted by a capital letter, so we say A, if that's what we're calling this particular one, and then the probability of that event is P, and with A in parentheses. Okay, probability rules. The first one that we encountered was that all probabilities are going to be between 0 and 1 inclusive. Remember the word inclusive, which if you wrote it as an inequality, that means that it's going to be P, the probability of A is greater than or equal to 0 or less than or equal to 1. 0 indicates it will never occur. 1 means it will always occur. Okay, and if we talk about the entire sample space, it has to add up to 1, like our normal distributions. Everything underneath a normal curve adds up to 1. The probability of a sample space has to equal 1. So everything inside there, all those probabilities added up equals 1, or 100% of the sample space. Okay, the probability that an event A does not occur is 1 minus the probability that it does occur. And sometimes that's much easier to go this route when you're figuring up a probability than counting up a whole bunch of individual probabilities. We put the little c at the top in the exponent position, but it's not really an exponent. It just means a complement. And notice that complement is spelled with C-O-M-P-L-E rather than an I, because we're not talking about having nice hair here. Okay, in the example I give you, when flipping 2 coins, the probability of getting 2 heads is 0.25. The probability of not getting 2 heads is 1 minus that, which is 0.75. Okay, the next thing we talk about is disjoint events. If A and B are disjoint, they have no outcomes in common. Okay, and so the probability that A or B occurs is the probability A occurs plus the probability that B occurs. And so notice that if we put or, if you can say the word or, then you're adding them together. Okay, if you need to back up and review this, please do, but this is very important. Okay, the example, let A be rolling a die and landing on an even number, and B rolling a die and landing on an odd number. They can't happen at the same time. The outcomes are listed here. A is 2, 4, 6. The outcomes for B are 1, 3, 5. And these events are disjoint because they have no outcomes in common. If you were to draw a Venn diagram with these, there would be no overlap. So the probability of A or B landing on either an odd or an even or odd, equals the probability of A plus the probability of B. Okay? Okay, now let's talk a little bit about independence. Independence cannot be shown with a Venn diagram. Just want to get that out of the way right now. They're independent if knowing that one occurs does not change the probability that another occurs. Example, roll a yellow die and a red die. Event A is the yellow die landing on an even number, and B is the red die landing on an odd number. One's not affecting the other. They are independent because the probability of A does not change the probability of B. Okay, if events A and B are independent, this rule down here establishes that they are independent. We're going to use this rule to check for independence. We can say this, that the probability of A happens and the probability of B happens. If we can put the word and in there, then we have to remember we multiply. Okay? So the probability of A and B equals the probability of A multiplied by the probability of B. Alright, and this particular formula is our test for independence. In a problem, they will tell us, oh, the probability of A and B is this, and the probability of A is this, and the probability of B is this. Are they independent? They'll give you all three parts. You plug it in, you check it out, and see if they're independent or not. One side has to equal the other. Okay, our example for this one. The probability that the yellow die lands on an even number and the red die lands on an odd number. So, in a die, half the numbers are even, half are odd. So we have 1/2 times 1/2. They are independent of each other, so the probability is 1/4. Okay, the next one. If the events A and B are independent, then their complements are also independent. And A complement of C is independent of B also. Okay? And I think we're getting into conditional probability, so we'll hold that for our next lesson. Please refer back to your book and this video if you need any additional assistance. And note that I will be including with this video some note sheets that you can either print off or use in class.